Hello, everybody. Good afternoon. I'm so happy today to introduce to you Dr. Ross. Andrew Ross did his bachelor's at Penn State and did his master's in Penn State. But when I was looking at his CV, I thought, wow, that's really cool. He got his bachelor's in 2013 and got his master's in 2013. I suppose this was an accelerated program. I didn't ask, but I'm assuming this must be an accelerated BSMS program. And he got his PhD in 2017 under the guidance of Ray Najjar. So it's great to have you, Andrew, here. And I really enjoyed reading Andrew's paper on the machine learning, which is got the same kind of topic he's going to be presenting today. And I thought this would be something which we could all benefit, especially for people who are working on Long Island Sound. The machine learning, we've been slow catching up on in terms of machine learning, but it also applies to everywhere else. So without further ado, Andrew, please welcome. Thank you very much for coming.
Yeah, thank you very much for having me. Great, so thanks for having me here today to talk about dissolved oxygen in Chesapeake Bay. I also thank my supervisor here at GFDL, Charlie Stock, as well as my funding from NOAA's Integrated Ecosystem Assessment Program and the Climate Program Office. So we're talking about dissolved oxygen and hypoxia, which is probably many of you may know has become increasingly a problem in many coastal areas. I borrowed this figure from Brightberg et al. 2018, showing different regions along the coast globally where low oxygen concentrations have been observed. So practically everywhere along the coastline. This is a problem for many different reasons, but primarily for fish habitats. Different fish species have different requirements for oxygen. Many cannot live below certain levels of oxygen. So 2 milligrams per liter is the threshold for hypoxia that I'll kind of use for this talk. Although different species have different levels, striped bass tend to require much more oxygen. Some species are in between. And as examples of coastal regions that experience hypoxia, of course, you're familiar with Long Island Sound. Experiences hypoxia many summers, particularly in the western part, closer to New York City. Mississippi River experiences frequent hypoxia in the summer, following extensive nutrient inputs from the Mississippi River. And similarly, Chesapeake Bay, so the focus of this talk, which experiences hypoxia every summer, also following nutrient inputs, this time from the Susquehanna River. So this is kind of sideways. Susquehanna River is here at the head of the bay. You can see this chart, we have pretty extensive low oxygen throughout the bay in the summer. This is an example from early July of last year. You can see it's kind of concentrated along this deep central channel in the bay. So it was early July, this is late July last year. A little bit of missing data here, but you can see there's even more hypoxia and practically anoxia here along the deep central channel of the bay. And vertically that sets up as being concentrated towards the bottom. So there's a density stratification, there's like a pycnocline right along this point here, and an oxycline to go with that. And below that, we typically have hypoxic or anoxic water in the summer. So there's a couple different causes of this kind of coastal and estuarine hypoxia, but most commonly it's associated with high loading of nutrients like nitrogen and phosphorus, primarily but not entirely from, say, fertilizer runoff. So that delivers a lot of nutrients to the bay. You get a phytoplankton bloom associated with that. That bloom essentially eventually sinks, and organic matter with it sinks to the bottom. It decomposes, that uses up oxygen, so that draws down oxygen in the lower part of the water. At the same time, there's a pycnocline, partially set up by that freshwater discharge, increasing the density stratification. So that prevents a vertical mixing of the water. It prevents oxygen from the surface from mixing down towards the increasingly hypoxic bottom water. With these different drivers, the amount of hypoxia that occurs in a given year can vary. So I've shown this example figure from Test et al. 2017, showing July 2011 in the Bay, when we had one of the worst hypoxia years on record. So pretty extensive hypoxia, almost from the head of the Bay, almost to the mouth, and again, mostly along that deep central channel. Compare that to July 2014, when there was almost no hypoxia in the Bay, just a little bit along that central channel. So July 2014, the sampling occurred following one of the tropical storms that passed by and mixed up the water in the Bay and increased the oxygen at the bottom. So to kind of control this hypoxia, as well as some other water quality problems, efforts have primarily focused on reducing the amount of nutrients delivered to the Bay, especially nitrogen. So these are nitrogen loads delivered to Chesapeake Bay historically. So in 1985, we had quite a bit, and it's been gradually going down between 2009 and 2019. Although still not to the level, so this black line here is the water quality goal for 2025. So still not quite meeting those water quality goals yet. And you can see the majority of this nitrogen comes from agriculture, with some from wastewater and a few other sources. So given these kind of controls on hypoxia, especially things like nitrogen loading, some studies have tried to set up forecasts to predict what the future hypoxia in the Bay will be. So this is an example from a group from the University of Michigan who puts out a forecast every summer. So essentially they look at the spring nitrogen loading using January to May nitrogen loading, and then use that to predict the hypoxic volume. So the overall integrated volume of water in the Bay that is below 2 milligrams per liter of oxygen. So you can see this example from 2019. Based on relatively high nitrogen loading, they predicted relatively high hypoxic volume for the summer. So that was that kind of a 1 to 2 month ahead timescale and integrated over the whole Bay. At kind of the opposite end of things, there's also been some studies using numerical models to predict short-term variations in oxygen. So there's a group at Virginia Institute of Marine Science that set up these 3-day hypoxia forecasts. So they build on top of NOAA's operational forecast systems that model temperature and salinity and currents for the next 3 days. And they add a simple oxygen component on top of that model. So it just treats oxygen as a passive tracer with a constant sink, so a constant respiration rate, and then it's set to saturation at the surface and the boundary. So a lot of my research in general has been trying to focus on doing more forecasts like these, particularly at space and time scales that are useful for like fisheries management decisions, water quality management, and other concerns in these coastal regions. So a lot of those take place, we're targeting kind of these week to month to year timescales, where decisions that are made also take place at roughly, say, 10, maybe 50 kilometer spatial scales. So both of those previous forecasts that I showed don't really quite meet these needs. So they're either a month ahead, but over a whole spatial region, or they're resolved in space, but only occurring at like a 1 to 2 day timescale. So the original goal of this study was to try to see if we could use like a machine learning type model to predict the summer hypoxia in the Bay. It didn't work out quite as well as I hoped, but there's still some things we learned from the study, and that's what I'll present here. So in this talk, I'll assess the drivers of sail flow oxygen predictions in the Bay at monthly timescales with the spatial variability resolved. I do this by building a machine learning model that predicts dissolved oxygen, and then looking at some of the features of this model, and then evaluating some alternative formulations that may or may not be useful for forecasting. So this is based on a paper that I published in 2019 in Estuarine, Coastal, and Shelf Science. So we used a machine learning model here. A couple of reasons for that. One is that machine learning models in general are less computationally expensive than a full numerical model. So the machine learning model that I use here, I can run it on a desktop computer. It takes a couple of hours to train, but then once it's trained, you can generate years worth of predictions almost instantly. Compared to numerical models, which would take on the order of half an hour to generate a single month's prediction on the same computer. Of course, machine learning models also handle things like nonlinearity as well as seasonality in the drivers of what you're trying to predict better than something like a simple multiple linear regression would do. And finally, since we're in Chesapeake Bay, machine learning allows us to take advantage of the unique Chesapeake Bay program monitoring data set, which has collected tons of observations in the bay since the 1980s. It also builds on previous work by Bart Malling et al. In 2018. So they used the same machine learning method that we're using here. It's called model trees to predict Chesapeake Bay temperature and salinity from global climate model data. So essentially downscaling global climate model predictions to predict surface temperature and surface salinity in the bay. They do this by taking information about the predicted air temperature as well as the river discharge from the Susquehanna River. You can see it worked out pretty well for them. So this left side here is the surface temperature. This is the observations, and this is the model predictions for an out-of-sample test period. And same thing for surface salinity on the right. So observed and then modeled. In both cases, matches the observed surprisingly well. So we're using model trees for this study as well. This is based on the Cubist package in R. So it makes things pretty easy to run. And I'll try to explain it in a very simplified manner that is hopefully easy to get through in a single talk. So machine learning method that is more common that you may be familiar with is classification tree, sometimes more generally decision tree. So you would use this if you want to classify your data, say whether your water is hypoxic or if it's oxygenated. To do that, you would take all of your data, develop some sort of rules to split the data. So say whether the temperature is above or below 10 degrees Celsius. Say it's cooler than that, maybe you just label your data as oxygenated. If it's warmer, maybe you would look at the density difference and decide if it's stratified, then maybe you have hypoxic water. Or if it's not, then you would predict that you have oxygenated water. So this is for classification. There's a similar method called regression trees, which works for predicting continuous values. So it's essentially the same tree, except here you're predicting a constant value at the end of each tree instead of giving a classification. One drawback to this method is that it does not work quite as well at predicting kind of the tails of your data because you're predicting this single constant mean value. So what we use here is called model trees, and it works more or less the same way, except instead of predicting a single value at the end of each tree, you fit a multiple linear regression model to the variables that were previously used to split the data. So here, at the end of these trees, you're using these different variables to predict what your oxygen will be. This, among other things, allows you to capture some of that tail values better. This kind of model would take a decent amount of data to train. And as I mentioned, we have the Chesapeake Bay program data set to do that. So this data set provides vertical profiles of temperature, salinity, and oxygen at, here we're using 126 unique locations, usually twice monthly in the warm season from 1984 to the present. So here I'm using 1984 to 2017. And even just looking at the warm season, so May to September, when hypoxia tends to be common, that gives us close to 17,000 observations to use. So for this paper and for this talk, I've divided it into two data sets. So I'll fit and train the models using data from 1986 to 2007. And then I'll use the last 10 years as an out-of-sample data set to evaluate the predictive skill. So I've shown on the right here the locations of those 126 different stations. For a few slides later in this talk, I'll kind of average the predictions and average the observations over some of these regions in space. So that's shown by the colors and the shapes. For example, we have an upper bay region, the lower bay region, this kind of core hypoxic region along that deep central channel where hypoxia is most common. And then a few for the tributaries that sometimes experience hypoxia. And then the remaining regions that, at least in the training data set, never experienced water concentrations of oxygen below 2 milligrams per liter. So what I'm predicting here is the dissolved oxygen, and more specifically, it's the column minimum dissolved oxygen anomaly. So I look at each vertical profile, determine the minimum dissolved oxygen that was observed. Usually that will be at the bottom, but not necessarily always. And then I'll look at all of the data for a station, fit and subtract a smooth seasonal cycle to produce anomalies. And in cases where we have multiple observations per month, usually 2 observations, I'll average those anomalies together for the station to produce a single value. So the reason for doing this is that oxygen in Chesapeake Bay has a very regular seasonal cycle. So it's always low in the summer and it's always high in the winter. But we're not really trying to predict that. We want to predict the interannual variability away from that seasonal cycle. And when fitting kind of statistical models or machine learning models to this kind of data, often that interannual signal can be drowned out by that strong signal associated with the seasonal cycle. And your model predictions would essentially just predict that seasonal cycle instead of what you're really interested in. So what I've shown here is an example from a station kind of in the lower middle part of the bay. This is the whole time series of dissolved oxygen. Here you can see, as I said, it's low every summer, high every winter, low, high, and so on. So what I do is look at the station data, fit it out by day of year, and then fit a smooth regression spline to that data. So essentially captures that mean seasonal cycle. And I subtract that, that smooth seasonal cycle from the data to produce anomalies. So I've shown here the anomalies from that data. You can see the seasonal cycle is gone, and there's that interannual variability that we're interested in predicting. So going back to some of the factors that contribute to hypoxia in the bay, you have things like nitrogen loading, the phytoplankton, the water temperature, which determines the respiration rates, the rates at which the organic matter from the phytoplankton is decomposed, as well as the water column stratification, the solubility of oxygen. Wind events can influence the stratification. They determine where the phytoplankton is transported. Stream flow to the bay also determines the stratification, as well as a couple of different other drivers. So our goal for this study was to try to build more of like a mechanistic model that we could kind of interpret a little bit. So we wanted to focus on these well-established drivers of hypoxia, rather than trying to do some more exotic machine learning where we have, you know, a wide variety of predictors with more dubious connections to hypoxia in the bay. So we used this total of 10 predictors to try to predict the oxygen in the bay with this machine learning model. The first one is just the column mean temperature anomaly associated with each oxygen profile. So the anomaly here is determined using the same smoothing method that I used for the dissolved oxygen. The second one is the density stratification anomaly. Again, it's the anomaly is determined using that same smoothing method. The density stratification is the difference between the density at the bottom and the surface. So a higher value means that you have more stratified water. Third, I looked at the mean sea level anomaly for a given station in the bay. That was averaged over the month. So it's kind of removes that tidal variability and just looks at the long-term sea level fluctuations. Fourth was total nitrogen loading from the Susquehanna River, totaled up over the previous 5 months. So if we're trying to predict a June dissolved oxygen, we would be looking at the January to May nitrogen loading, which is consistent with what some of those previous modeling studies have used. Fifth, we looked at the mean wind speed along the northeast-southwest axis, averaged over spring, so over February to April. So this paper by Lee et al. In 2013 suggests that that can influence the transportation of the phytoplankton in the spring, and that eventually sets up the hypoxia in the summer. Then we had a couple of coordinate variables, so things like month, hour, bottom depth, longitude, and latitude. So those allow the predicted response to vary over space and time. So just to summarize these methods then, first what I'm doing is developing a machine learning model that predicts the column minimum dissolved oxygen anomaly in Chesapeake Bay at a bunch of different stations from a small set of predictors with kind of established mechanistic connections to hypoxia. With this model, next I'll evaluate the predictive skill during the last 10 years of available observations, which were not used to train the model, so it's an out-of-sample test of the predictive skill. I'll use this model to identify key drivers of the dissolved oxygen variability, and then try to use it to forecast future dissolved oxygen. So I'm going to jump right into this evaluation of the model results. This is the correlation between the predicted and observed anomalies over all of those different stations in the bay, separated here by the month of the prediction. So you can see there's not too much variability in the skill over months. All of the purple regions indicate we have high correlations with the observed anomalies. And you see those dark purples over most of the locations. There are a few exceptions, so there tends to be a little bit less skill here near the mouth of the bay. So it's possible we're not capturing some of the exchange with the shelf waters. And then there also tends to be maybe a little bit lower scale here along the some of these stations in the central channel, where oxygen can be low and it can be hard to predict some of the deviations away from those low values. If we look at the bias tends to be pretty low at all the locations as well. One thing I'll note here that will come up again several times later is that we tend to have a low bias in July, August, and some places in September, particularly in the lower half of the bay. So here the model is predicting less oxygen than was actually observed. Lastly, moving on to the root mean square error, that also looks pretty good. All of the blue colors are root mean square error below 1 milligram per liter. And greens are also fairly reasonable performance. So to aggregate this, I kind of looked at target diagrams and looked at the average predictions over those different regions compared with the average observations from the same regions. And I've shown it here in target diagrams. So if you haven't seen these before, they plot the centered root mean square error, or the unbiased root mean square error, compared with the bias. And then, so the total distance from the origin here is equivalent to the total root mean square error. So the idea is that a lower root mean square error will be closer to the origin. And then these values are standardized so that a value of 1 has the same total root mean square error as using a prediction of just a long-term climatology. So the idea is that to have skillful predictions, you would be inside this circle, and ideally as close to the origin as you can get. And for the most part, most of these points are inside the circle, so we do have skillful predictions during this testing period. You can see we tend to have a little bit of high bias in May, and then that bias becomes negative in July and August, as I mentioned earlier. You also see that predicting in that core hypoxic region, that deep central channel, is a little bit more challenging. Although overall, the predictions are still good because we're predicting low oxygen and we're observing low oxygen, but we're not really capturing that very small variability away from those low oxygen values. Last thing I'll notice here is that the way the centered root mean square error is defined, a negative value indicates that the model predictions have a lower standard deviation than the observations, which is what we see in most of these points. So the model is kind of capturing some of the variability, but it has a little bit of a damped variability relative to the observations. So since we have reasonably skillful predictions with this model, next I'll look at which of the input variables to the model are the most important. So one metric for this is to look at the percent of the rules and the regressions in the model tree that each variable was used in. So if you remember the model tree, we split that data based on different criteria and fit regression models to those different subsets of the data. So you can look at how many times a variable was used to either split the data or fit those regressions. And that gives you some measure of how important the variable is. So overall, we see that the density stratification is the most important variable. That little square there should be a delta. So density stratification is used over 75% of the time, either to split the data or to fit a regression model. Next up, we have the latitude and the depth. So these kind of modulate the response based on whether you're closer to the head of the bay or the mouth, and then whether you're in deep or shallow water. Fourth, we have the mean temperature, which occurs in just over half of the models or splits. Then variables like mean sea level, spring winds, and nitrogen loading are comparatively less important. Second way to look at the effects of these different input variables is to look at the partial dependence. So essentially this is the effect of one or more variables averaged over the effects of all the other variables in the model. So given your model and it's one or more variables S that you're interested in looking, calculating the partial dependence for, you can look at the mean value of your model predictions averaged over all of the other variables that go into your model. So you can essentially fix all of the density stratification values that you have to a single value, say 5, and then use the model to predict based on all the other observations that you have the density stratification, and then average those results together to get a single value for what the average predicted dissolved oxygen will be. So if we do that with the density stratification, you can see as the fixed value of stratification is increased, So as the stratification becomes stronger, the water column becomes more stable, and there's less mixing. We see that the model does predict less dissolved oxygen, pretty significantly less. Same thing for the mean temperature. So as we increase the mean temperature that goes into the model, the predicted dissolved oxygen decreases. I've shown here just two of the other variables in the model. So mean sea level, we don't see a really strong signal. It's hard to tell what it's fit here on average. And then for spring winds, we see a smaller signal, but we do see that as the spring wind becomes more positive, the predicted oxygen becomes more negative. So the way that I defined the spring wind here is that a positive value is a wind that is coming from the northeast. A negative value is coming from the southwest. So this result is consistent with that Lee et al. Paper that proposed the spring wind is one of the mechanisms influencing hypoxia in the bay. The final thing I'll note here is that the y-axis for each of these plots is different. As you can see, density stratification goes from 4 to -3 or so. The spring winds are much smaller, going from, say, 0 to -0.2. So primarily, it's the density stratification that's determining the oxygen in the predictions, and to a lesser extent, the mean temperature. So that's a little bit of a problem if you're trying to use these to forecast future values instead of just predicting the values that you have right now. Because the way it was defined, the density stratification and the temperature are at the same time as you're taking that oxygen profile. So you have to know those at the time of your prediction. And you can't really use these to forecast future conditions unless you had forecasts of future stratification and future temperature. So I did try testing 2 different alternative models that replaced those 2 temperature and stratification variables. One used the previously observed river discharge. So river discharge is correlated with the stratification because that fresh water will increase the stratification. And I also looked at the previously observed dissolved oxygen, so kind of as like a lagged or a damp persistence type effect. So I've shown these here. This is the target diagrams when I use the previously observed river discharge in the model. You can see basically all the points are along that circle where there's this, that's the boundary of model skill. So essentially, we don't really have any prediction skill here, with the possible exception of mid-September. And if we looked at the models using previously observed oxygen, the skill is actually slightly even worse. Now we don't even have skill in September. And many of these predictions are far outside the circle. So neither of these models would really work for trying to forecast the future oxygen in the bay. So really, we really need to know the stratification. The stratification is the strongest predictor of oxygen in the model. So one of the things I tried to do is to see exactly how well we need to know the stratification in order to predict the oxygen well. I did this by adding small amounts of noise to the stratification observations in the testing data set, and then looking at how the root mean square error of the predictions degraded as that noise was increased. So the x-axis here is the standard deviation of the random Gaussian noise that I added to the density stratification anomalies. And then the y-axis is the root mean square error relative to the climatology. So values below 0 indicate forecasted skill, which, as those target diagrams I showed before show that we do have. As you increase the stratification noise, that skill goes away. Generally, we need to know the density stratification with an error of no more than about 0.5 to 1 kilogram per cubic meter. So if we could forecast the stratification with that kind of accuracy, we would have some hope of being able to forecast the dissolved oxygen in the bay. Another important effect that the model identified was the water temperature. So water temperature does a couple of things to the oxygen. Water temperatures can increase the respiration rate, so it affects the biological activity in the bay. At warmer temperatures, the oxygen can be drawn down faster. One of the other effects is the solubility. So at higher water temperatures, the solubility of oxygen in water is lower. And the model doesn't necessarily know which one is which, or what is causing the effects on oxygen. But it's interesting to note that the model predictions are roughly lined up with the effect of temperature on solubility. So I've shown the red line here, that partial dependence line that I showed before, showing as you increase the temperature anomaly, the predicted dissolved oxygen concentration goes down. And then the blue is the solubility curve for oxygen in seawater as a function of temperature. So these two line up pretty well, which would kind of support the idea that we're mostly seeing an effect of solubility here in the model. The third thing, and one thing we were kind of a little bit uncomfortable about, or tried to be very, very careful about how we say this when we published it, was that the modeled effect of nitrogen loading was pretty small. Nitrogen loading didn't have a big effect on the predictions, which is kind of contrary to the idea that we need to reduce nitrogen loading to the bay in order to improve the water quality. But it is consistent with what's been found in previous studies. So the study here in 2004 found an R squared of just 0.17 when comparing the July hypoxic volume with the January to May nitrate loading. Similarly, Murphy in 2011 found R squares of only 0.08 or 0.21 when comparing the early and late July hypoxic volume with total nitrogen loading. And then this model by Scully and evaluated by Irby et al. In 2016, which is kind of the basis of that 3-day oxygen forecast that I showed in the introduction. So they use just a simple numerical model that has that fixed respiration rate. It doesn't capture the interannual variability of biology in the bay. And that model is nevertheless able to skillfully predict the variability in oxygen, primarily by predicting the stratification. So we had to be careful about this because we want to emphasize it does not mean that the nutrient loading does not cause hypoxia. Nutrient loading is correlated with another driver of hypoxia, the stratification produced by river discharge. So it can be difficult for the model to pull out the effect of nitrogen loading alone. Secondly, the recent interannual variability of nitrogen loading is pretty small relative to the nutrient reduction goals that will reduce hypoxia and improve the water quality in the bay. So we're targeting something like a 40% reduction in nitrogen loading to the bay, which is much smaller than what we've observed recently. And so just as a point of curiosity, I tried running the model with the historical time series of all the observations, except with the nitrogen loading reduced by 40%, so trying to meet that reduction goal. This isn't necessarily a valid comparison because here we're really extrapolating with the machine learning model far beyond the data that it was trained on. So it can do some weird things. But I thought it'd be interesting to look at anyways. So we do see in the upper bay in that core hypoxic region, as well as in some of the central tributaries like the Patuxent and the Potomac, that reducing the nitrogen loading going into the model does improve the oxygen. Although again, I really want to emphasize that this is just an extrapolation and not necessarily a great prediction. And finally, the other point that I make in the paper is that going back to these different inputs that go into the model, these 10 different mechanistic drivers, the only one that we can really control is the nitrogen loading. We can't really affect the mean temperature. We can't affect the sea level. We can't affect the stratification unless we add, things that mix the water column throughout the entire bay. So we really need to reduce the nitrogen loading in order to improve the water quality in the bay. As a point of discussion, some of the changes in oxygen that have been observed over time may not be able to be captured by the model. There's some non-stationarity that we're not able to capture, or some mechanisms that we don't capture. One of these changes is that the late summer hypoxia and anoxia has been improving. This is a figure from Testa et al. 2017, showing some declines in the late summer anoxic volume, as well as the decrease in the anoxic volume that you get as a function of the January to May nitrogen loading. So given amount of nitrogen loading now will produce less anoxia than it once did in the 1980s and 1990s. Similarly, there's been observations of kind of an earlier breakup of hypoxia and increased late summer oxygen concentrations in that lower middle part of the bay. So this here is from Testa et al. 2018, showing some regions in the kind of lower middle part of the bay and the oxygen concentrations increasing over time. And I think this is at least partially due to the increase or the decreased nitrogen loading that has been achieved as a result of those water quality programs. And that goes back to the target diagrams that I showed before. So we had a negative bias developing, especially in July and August, and also to some extent in September, particularly in that kind of core hypoxic and lower bay regions. So in this part, the model is predicting that there will be less oxygen than was actually observed. So that would be consistent with the idea that the oxygen has been improving over time in these regions, and that the model is not able to capture whatever it is that's driving those improvements. As a second point of discussion, some of the pros and cons of using this machine learning model compared to some other methods. So compared to linear regression, obviously one of the advantages is that we can capture things like nonlinearity. However, it's also easier to handle seasonality in the drivers of oxygen and time-varying drivers in general. So for example, Test et al. 2017 tried to predict the anoxic volume with linear regression using two different models. So they have a different model for early summer. That one looks at things like nitrogen loading, stream flow, sea level, the southeast wind direction. But the late summer model only uses the nitrogen loading. So they kind of do this manual model fitting. With the model trees, we can include the month as a predictor that goes into the model. And that allows the model tree to decide on its own how to split the data and whether some of these drivers will change over time as a function of the month. Compared to more complicated numerical models, machine learning models still provide lower computational costs. As I mentioned, the training takes an hour or two, and then you can generate predictions almost instantly. At least in some cases, the models may have fewer parameters. It depends on your model, but it's easier to train or calibrate than it is a full numerical biogeochemical model. You can do cross-validation pretty easily with a machine learning model. On the other hand, these machine learning models provide less reliable extrapolations, as I noted with that simple experiment with the nitrogen loading. It's possible that you can extrapolate far beyond the range of your training data. So you wouldn't want to use this necessarily for climate change simulations. That last point kind of points to one of the ideas that I've had for future research, that would be combining a machine learning and a numerical model. So I have a second paper that I published a couple months ago that develops 35-day numerical model forecasts for Chesapeake Bay, driven by 35-day weather forecasts. This is kind of that numerical model domain on the right here. With this numerical model and driven by these weather forecasts, I found that we could skillfully forecast the water temperature in the bay for at least the next 2 weeks in advance. And we were also able to forecast some of the stratification in the bay. However, this particular model didn't have any skill at predicting the oxygen. So it used that model very similar to that simple respiration model. So one of my ideas for future research is trying to see if we can combine the predictions from this model, the predictions of temperature, salinity, and stratification, with the machine learning model predictions of oxygen. So some final points then, just in general, in Chesapeake Bay, we can get skillful predictions of dissolved oxygen using the machine learning model. And the stratification and, to a lesser extent, the water temperature are kind of the keys to getting a skillful prediction from this model. If we wanted to forecast the dissolved oxygen rather than just predicting it at the present time, we would really need to have skillful forecasts of stratification. And that's all I have. Thanks again for inviting me to present, and happy to take questions.
Thank you very much, Andrew. I'm looking at the chat. No question. I have a question on here. So
Sure.
with the stratification and also that can be split because of temperature and the salinity. And you somehow did that in a roundabout way by putting in discharge, but you think the results would have been different by just putting salinity directly?
So instead of
using river discharge.
Yeah. Like for these models, instead of using the previously observed river discharge.
Right.
I guess, yes, the idea of using the previously observed river discharge was that it had like a lagged correlation. So the last month's river discharge would set up this month's stratification. Whereas with salinity, I mean, you would need to know this month's salinity to determine this month's stratification. So that was the idea for using river discharge here.
But is that the same thing that was applied in terms of wind? Because with what Yonju Lee did with the wind, was the wind from the previous month or the current?
The wind that I used here was from February to April. So averaged over February to April. So we were looking at predictions from May through September.
Okay.
Yeah, one of the reasons for not including other wind speed and wind direction variables here was that we didn't think we would be able to forecast those as well, even with the numerical model.
Okay. So I suppose even with salinity, you could do it with the previous times, you know, lag it, right? And then get the same thing.
Yeah, it's possible there would be some sort of lag correlation that way, yes.
I'm looking at the, anybody with a question, you can raise up your hand or type in the chat. I'm looking. Going back to the mid-lower bay, you did give some reasons, but I was trying to write notes. I didn't quite get them. Can you go back and say why the predictions there were weak?
So do you mean like this tendency to have a low bias, especially in July and August?
Right. No,
yeah, so that's
the dotted the map thing, the map figure you had. Yeah. Yeah.
So like these figures.
Right.
Especially the correlation.
Yes.
Yeah.
So in the middle, it's kind of weakish.
So these points here, yes, I mean, some of this I think is because, so this is where the hypoxia tends to be the worst. So essentially, well, part of it's at the lower limit of detection. You know, like we can be essentially anoxic here. Some of it is that it's like trying to predict. There's only small fluctuations that occur, and the model is not as capable of predicting those small fluctuations. So it's like a difference between like minus 0.5 or 0.5 milligrams per liter and 0.75 milligrams per liter. Like a small difference like that is more challenging to predict, I think.
Okay.
I don't know if that makes sense, but that's how
it kind of makes sense. You've got a very weak signal to begin with, but then
right.
is that an inherent handicap with the machine learning strategy?
I mean, I think it's a problem in general. Like that numerical model that I used also has pretty weak skill at predicting oxygen in these deep central channel regions. And again, I think it's just because it's consistently low every year, and there's not a whole lot of variability away from that. And the variability that does occur is pretty hard to predict. Like, you know, it can be just a passing wind event or something like that that stirs it up a little bit.
Right. I have a question from Hashali, and it's what actions are being taken to minimize nutrient loading in the Chesapeake Bay?
I mean, that could be the subject of a whole talk, but there's, going back to the introduction slide that I presented, where a lot of the loading is coming from agriculture. So there has been a lot of efforts to get different management practices to reduce the amount of loading that comes from agriculture. There has been, you can see the wastewater and combined sewer overflows have decreased a lot. So there's been a lot of efforts to upgrade water quality treatment plants, reduce like sewer overflows to the bay. I guess I would say that those are probably some of the two main efforts, but there's a whole a program to do different water quality improvements.
Right. Well, I don't see any other question from the audience. Thank you very much, and we really appreciate this. I'm gonna follow up.
Thanks again for having me to present.
Thank you. And thank you everybody for coming.